In this video, we're going to be taking a look at two practice problems that involve buoyancy, the force of tension, and using some of Archimedes' principle as well. So in orange here on the left, we have a sphere that's hung by a string and then lowered into a bucket of water until it is completely submerged. What is the radius of the sphere if the string has a tension of 35 newtons? So we have a string with a sphere attached to it. It is 5 kilograms and it is in a container that is filled with water. All right, so there's our initial drawing right there. And let's go ahead and label some of our forces so that we can start to set up an equation and then plug some variables in. So of course we have the force of gravity pulling straight down as usual. We have our force of tension from the string that's got to be pulling it up. And then in addition to that force of tension, we have a buoyant force applying a force upwards as well, which means that if the object is static, is at rest, then we have the buoyant force plus the force of tension pulling it upwards. And then we have the force of gravity counteracting that. So we're going to subtract it. And that would equal 0 newtons in total to keep it in static equilibrium. Now from there, we're going to break our formulas apart and put in some different values as well. So for the buoyant force, we're going to use the formula rho Vg. For the force of tension, we know that it's 35 newtons from the problem. And for the force of gravity, we know we're going to use mg. So from there, let's go ahead and plug in some values. We know the value of rho, the density of water, is always 1,000 kilograms per meter cubed. For the volume of the sphere, that's unknown. We have a constant g value of 9.8 plus 35 minus 5 times 9.8. So what we can do here is we can go ahead and combine these two, and we would get negative 14, which means that if we add 14 to each side, then we have 14 equal to, and then we'll take 9.8 times 1,000, and then we get 9,800 as our coefficient that is in front of the v. And then we can go ahead and divide both sides by 9,800, and then that's going to give us our volume of 0.0014. All right, so we're almost there. We know that our volume is 0.0014. So what we can do is we can take 0.0014 and then set that equal to the volume of a sphere. So we have 0.0014 equal to pi r cubed, the volume of a sphere. And then we do a quick algebra step or two, divide each side by pi. And then we are going to cube root this final value. And then we get a final radius of 0.076 meters. So after you divide 0.0014 by pi, what you can do is if you can find a cube root button, go ahead and use that. If not, you can raise it to the 1/3 power, and that would be the equivalent of taking the cube root. and then you would go ahead and find your radius from there. So to sum things up, what we want to do is if we're working on a problem like this, we're going to have our force of gravity as usual, and then our buoyant force as usual if it's a buoyancy type of problem. And then we want to make sure we are aware of which way the force of tension is pulling. In this case, since it's attached to the top part of the sphere, that means the 5 kilogram mass is trying to sink and the force of tension is restricting it from sinking. So it's going to help with that upward force. And then once we set everything equal to 0, because it's all in static equilibrium, we can break apart each of our formulas, plug in our numbers, and then do a little bit of algebra to solve for our radius. Okay, so let's go ahead and clear this work away from our first problem and take a look at our second one. Now for our second problem, we have a 0.3 meter cubed 20 kilogram ball that's attached to a string from the bottom of a container filled with water. What is the force of tension in this string? So for this particular one, we have an object that is trying to float towards the surface, and we have tension that is pulling it downwards. So in this case, we have the ball that's submerged in water, and we have the force of tension pulling it downwards, and we also have the force of gravity pulling down as usual, and then counteracting both of those is the buoyant force, the weight of the water that's displaced by that sphere. So in this case, we can go ahead and set up our formula as FB minus the sum of our two downward forces, and that's equal to 0 newtons because the object is static. Now, what we can do is break everything up into our formulas. We have rho Vg minus mg minus ft equals 0. And what I can do is I can go ahead and add ft to both sides. So I can have ft over here because I'm looking for the force of tension anyway. So I want to go ahead and isolate that. And I have the rho of water, 1,000 kilograms per meter cubed. We have the volume displaced, 0.3 meters cubed times a constant 9.8. And then we can go ahead and subtract the mass of the ball, 20 kilograms multiplied by 9.8. So find the product of these three numbers. We have 2,940 newtons minus the weight of 196 newtons, and that will give us our final force of tension. All right, so for this one, it seemed slightly less complex, especially after doing the first one. We didn't have to use any additional formulas like the area of a sphere. All we had to do is draw in our forces, use Newton's second law, which is taking the sum of the forces and setting it equal to mass times acceleration. But there is no acceleration in this case, so we have a total of 0 newtons off to the right. And then break everything into our formulas, and we were able to just kind of plug in everything we needed, and then take the difference of those two values, the buoyant force and the force of gravity, and that gave us our force of tension of 2,744 newtons. So I hope that was helpful to you in analyzing some problems with buoyancy and tension. Thank you for watching and listening.